p-dopants for silicon. Okay? So let me just show you the cartoon of that. So here's boron. Boron is on the left of silicon, but up one column. It just turns out it's easier to put boron in silicon than it is to put aluminum in silicon, but you can do both. So with boron, the boron has an overall negative charge, analogous to the phosphorus having a positive charge. And you see that one electron is missing from the otherwise filled band, which constituted all of the electrons being tied up in covalent bonds. Okay? So the next thing we need to do is we need to ask about the dynamics of our electrons in our holes once we have them. So let's do that. So again, drawing exactly the same. Maybe I'll use. I'm going to make my life simple by just erasing this stuff here. A little bit of eraser transform. So here we have an insulator or a semiconductor. We have a filled valence band. We have a gap. We have an empty conduction band. And let's imagine that either by doping or by optical excitation, we can put an additional electron up here in the conduction band. Now, as we mentioned, this K here need not be zero. It can actually, the minimum of the energy of the conduction band can occur at any point in the Brillouin zone. Sometimes it's zero, but sometimes it isn't. So you have to keep that in mind, that it can really be at any point. So it's conventional, and we've done this before, to define an effective mass via 1 over m star sub electron. So it's the electron effective mass is 1 over h bar squared d squared energy dk squared, evaluated at k equals minimum energy, well, what should we call it, K min. At whatever k the parabola has its minimum. K equals K min. Yes, I'll just K equals K min. Okay? And with this definition, you then have the energy as a function of K can be expanded around this minimum energy, E min, plus h bar squared over 2m electron star, K minus K min squared. So we defined the effective mass in this way, such that this thing would look like a free particle, h bar squared K squared over 2m. Now, two things to keep in mind. One is that it's not the bare electron mass. It has to do with the particular structure of the band, exactly what the curvature is of the band at the minimum. And secondly, the minimum momentum, the minimum energy momentum need not be at k equals 0. And third, we really need crystal momentum, not real momentum here. But the reason why it's sensible to talk in terms of this effective mass is given by calculating the group velocity. So the group velocity is d omega dk, which I can write as 1 over h bar dE dk, just from the relation between d and omega, which is then h bar over m star k minus k min. So that means if you displace the electron from the minimum of the band and you displace it to the right, you give the electron a group velocity moving off to the right. And if you displace it from the minimum energy to the left, you give it a group velocity moving off to the left. And the relationship between the momentum and the group velocity is given by the effective mass. So this gives us a right to call this thing an effective mass. Now, there's a little bit of complication in 3D, or in 2D. In 3D, most generally, you would have something which is quite ugly, E equals E naught plus, well, you have to remember these things are vectors, so they have indices, and k minus k min sub I, some matrix alpha ij, k minus k min sub j. Then you can diagonalize the matrix alpha here. You would get 3 orthogonal vectors, and you would have 3 possible effective masses in the 3 different directions, and you would generally have anisotropic effective masses. However, for our purposes, for simplicity, we're going to assume isotropic, and many materials do have isotropic effective masses, in which case, in 3D, we have E equals E naught plus h bar squared over 2 m star electron k vector minus k vector min squared. Okay? So this complication of having anisotropic material does occur, but we're going to ignore it. All right. Now we can do something similar for the case of holes. It's probably worth me drawing that diagram again, since I just slid it off the top. So here's the valence band, here's the conduction band. Now, suppose that the valence band is completely filled, but I'm going to add 1 hole to the conduction band here. Okay? The conventional definition, which I approve of, is to define effective mass of hole. Define effective mass of hole via 1 over m star hole equals 1 over h bar squared absolute d squared e dk squared evaluated at k equals k max. In other words, at the top of the parabolic curve. Now, this definition always gives me m star hole greater than 0. And there's a good reason for that. In some books you will find will define the effective mass of a hole to be negative. And although you're allowed to define things any way you want, you have to make up for that minus sign somewhere else if you do that. I think physically it makes a lot more sense to define the effective mass of a hole to be positive. And even though the curvature of the valence band is sort of opposite the curvature of the conduction band, and I'll argue why it is that thinking in terms of positive hole mass is really more useful. So, let's see if I can do this. So, I'm just going to draw the valence band here. So, first we should ask, where in the valence band do you put the hole in order to have the minimum possible energy? Well, E min occurs when the hole is on the top of the valence band, right? This is like the air bubble bubbling up to the top of a glass of water. The electrons want to sink down to the bottom of the band, so the hole comes up to the top of the band. So E min is the electron, the hole sitting at the top of the band at energy E min like this. Okay? Now, if I then take this and I displace it by some k in this direction, so this is, let's call this k min, this position k min here, bottom k. If k is, so this is k min. Then I want to displace it to some other k, to this point here, and now put the hole at this point here. The E sub k will be E min plus h bar squared over 2 m star whole k minus k, oops, did I call that k min? I meant k max. This should be called k max, because it's the maximum energy in the valence band. Call it k max. Oh my gosh, now I'm getting confused. So it's the minimum, maybe it's called this evalence. That'll make my life easier. Call it evalence. E sub valence, the top of the valence band energy. So the amount of energy that this hole has actually increases as you push it down into the valence band. Try to understand this a little bit more intuitively. It's like pushing a balloon underwater. The balloon wants to be on the top of the valence band because the water wants to be as far down as possible, so the hole wants to be as far up as possible. It takes energy to push that balloon underwater, to push it down to a lower point. So the absence of an electron wants to be at the top of the band. The hole wants to be at the top of the band. It takes energy. It takes an increase of energy to push the hole down into the valence band. So as a result, so with this equation here, the energy is actually increasing as you take K away from its favored position here. It looks exactly like what we have for the electron, and again, it looks like a quadratic spectrum. It looks like a free particle with a positive mass. And we can justify treating this as a particle with a positive mass, again, by calculating the group velocity. dE dk is h bar over m star whole times k minus k max. So if you displace the hole to the right, you're giving it a momentum and a velocity moving to the right as well. And if you displace the hole to the left, you're giving it a momentum and a velocity to the left as well. Okay? Is that clear? Did I confuse everyone? Yes? Good? Okay. See some people nodding, and I assume that represents everyone. Okay. All right. Now, finally, if we understand the masses of these particles, we can move on to understand the dynamics. Okay, so how do we figure out the dynamics? Well, the easiest way to study dynamics is to go back to Drude theory, which we studied, which is very classical theory we studied at the very beginning of the term. So let's do that. We'll write down for electrons a Drude equation, which is just really m electron star v dot. So this is ma equals force equals F equals ma, equals minus E electric field plus V cross B. And then there's a drag term or a scattering term, mass of electron, velocity